Mr. Okechukwu, can you see it clearly? Can you see the board clearly? I don't know if it's clear enough. I'm trying to work on it. Mr. Yeke, can you see it clearly? I don't know if it's clear enough. Okay, please. If you are just joining, just double tap on the screen to give it a thumbs up. Thank you so much. Double tap on the screen. Uchechus, thank you for coming. I really appreciate. Please, let's give it a thumbs up. Okay, thank you so much. Now we can. Good day, everyone. So today I'm going to look at a topic under SS2 first term, moment of a force. I did part of it last weekend. I did equilibrium of forces. There we actually looked at the triangle of forces, how we can represent a triangle when three forces are acting at a point. Okay, but today we're going to look at the moment of a force. So let's go to the definition, then I can explain it further. Moment of a force about a point C is the turning effect of the force about that point. It is equal to the product of the force and the perpendicular distance of each line of action from the point C. What am I trying to say? For example, if you get a tap, some of you have tap in your house. If you get a tap, now this tap, you only see the head up, rather the handle up, right? That is the moment we are trying to say now. If you turn that tap, it will now rotate. You're actually turning it with a force, because you can't just do the tap head this way and it will turn. You're going to apply a force. When you apply that force on that tap head, you will now rotate it. It will now move to cover a certain distance. That is the moment I'm trying to say. Okay? Even door handle is always like this, and we have one going down. So you now turn it with a force to be able to do what? Open the door. When you turn it, you're going to move a certain what? Distance. And that distance is perpendicular. That's what I mean. Now, if you are using this to make reference to this moment of a force, now you see that this is a bench. This is the center of the bench. From here, we have a force, F. The distance from here to the center is what you say to be what? D. But that distance is perpendicular. That is the moment. Perpendicular what? Distance. Okay? So we can say that it is equal to the product of the force. That is the force added to that object, or the weight acting on that object, and the perpendicular distance from this line of action, from the point C. So this is the force, then this is the center of what? Of the bench. Do we understand? So from here to the center, we have perpendicular distance. Why is it perpendicular distance? Because the force is acting down. Do we understand? The force is acting down from here to here. So we are asked to calculate the moment from this diagram. The moment M is equals to force times perpendicular what? Distance. So I can say this is just simply put force times what? Distance. Do we understand? Now, anytime you're considering the force and the distance and the perpendicular distance, if you have two people sharing this is a bench, and this is what? This is the middle. I call it the center, P. And a weight is hang here, and it's acting down. That is F. What will be the moment? Now, there's a distance from this center to where this force will hang. We have that distance to be what? D. So the moment from here to here is this force that is acting down, and the perpendicular distance. Why do we say perpendicular? Because the distance and the force acting down is perpendicular. Perpendicular means it is acting at right angle. That is perpendicular distance. The distance is perpendicular to the what? To the force acting down. That is what I mean. Okay, so if I move further to explain this second diagram, we are going to have that this particular bench, this is a bench, but the force is inclined. Now, since it's inclined, we are making respect to vertical and horizontal components of this what? Of this moment. Okay? Now, if you're making respect to the horizontal components, you are going to make use of cos theta. Now, this thing I'm just explaining now is under resolution of vectors. That is a situation whereby we resolve vectors into horizontal and vertical components. And if you don't know how to resolve a vector into horizontal and vertical components, you can check up my previous video in my channel where I did resolution of vectors into horizontal and vertical components. It will give you an edge to understand this particular thing I'm trying to explain. Because this force is inclined, no longer the one that is what? Perpendicular. As this one is inclined, we are making respect to what? Resolving this force, horizontal and vertical what? Components. Okay? So for us to resolve it, the moment here will now be F cos theta times what? Distance. This one is when we are resolving to the horizontal component. That is in respect to horizontal. In respect to horizontal component. While the respect to vertical component is what? D sine theta. So the moment too will also be F sine theta times what? distance. Do we understand? So that is what we can say under what? Moment. I'm going to sketch it again and explain further. All right. Angela, thank you for stopping by. I really appreciate. Thank you for coming. Thank you. Thank you for coming. Okay, so we can proceed with what I have. Now, if we are actually looking at this moment of a force, there are things we should put into consideration. There are two factors that affect this moment of a force. One is the force, and the second one is the perpendicular what? Distance. Okay? So if we say that the moment m is equals to force times what? Distance. Now, how do we get the units of moment? Now, units of m. Okay, first is measured in newtons, so that is my what? My n. Then distance is measured in meters. I have what? M. So the unit of moment is Newton meter. Now we must not forget that moment is a vector quantity. We know what is a vector quantity. It's a quantity that has both magnitude and direction. So this moment is equals to force times perpendicular what? Distance. And the unit is Newton meter. Newton meter. Then the moment is also a vector quantity. Now I can broaden this unit further. This is not the base unit of moment. So let me say base unit of moment. For us to get the base unit of moment, if I say Newton meter, we know that Newton is what? Is force. And force is mass times what? Acceleration, right? Then multiplied by what? By meter. Okay? So what is this my mass? My mass is measured in what? Kilogram. Then what is this my acceleration? It is measured in meter per second square multiplied by this meter. Okay, this is mass, while this is meter. So I have one. From the law of indices, what I'm going to do is to bring them together. I have meter, take one of the bases and add the powers, that is 1 plus 1 to give me this, right? So I have kilogram meter square per second square. This is the base unit of moment. But that does not mean that we cannot still use units of moment as Newton meter. Okay? But if you know this one, it will give you an edge to be able to denote the dimension of moment. In case you are asked, what is the dimension of moment? We already know that this is mass. We just have to write capital what? M. This is length. We just have to write capital what? L. We now put square on top. Then this is seconds, which is for time. We just have to write capital T minus what? 2. Now this is what? This is the dimension of moment. This is the base unit of moment. So don't get it confused. Let me say this is what? This is dimension. This is the dimension of moment. Why this is the base unit of what? Moment. We can still use moment as Newton meters. So I'm going to look at few examples under this moment so that we can proceed and go to another part of it. All right, let's look at what we have. Using the diagram below, calculate the moment of the force of 10 Newton about point P. So looking at this particular question, we are making respect of the moment. This is the moment. We are asked to find the moment rather. Now, the force acting is 10 Newton, but this is inclined at an angle of 30 degrees to the what? To the horizontal. Okay, then we have the distance covered to be what? 12 meters. How do we calculate the moment? And I told you, when a moment is inclined, that means we make respect to horizontal and vertical components. Okay, so from this particular question, we can see that this object, this force of 10 Newton is inclined at an angle 30 degrees to the horizontal. So for us to get the moment, we are going to say the moment is equals to F cos theta times distance, right? Then what is my F? My F is the 10 Newton. I will say 10 Newton. What is my theta? That is angle. The theta is 30 what? Degrees. What is my distance? My distance, D, is 12 meters. Now, if you have this, it's just for us to put it into what we have and solve our problem. Since we said that moment is the product of the force and the perpendicular distance, right? Okay, and this is the perpendicular distance. Okay, so let's go. M is equal to, I have 10 cos 30 times my D is what? 12. Okay, let's go. With the help of your calculator, you just say cos 30 is going to give you what? 0.866, then multiply by what? 12. So let's multiply all through to see what we have. 10 times 0.866 times 12. So my answer becomes 103.92 Newton meter. 103 0.92 Newton meter. So this is how we can solve this. And remember that this question was making respect to the horizontal component. Let's assume that they make respect to the vertical component by drawing what we have up, right? Or they say we should resolve it to the vertical component. Instead of using cos here, we are going to use what? Sine in place of cos. That is just the difference. Do you understand? So let's go to another part of the question. All right. This will be A and B, okay? Let's go to the principle of moment. The principle of moment states that if a body is in equilibrium, then the sum of the clockwise moments is equal to the sum of the anti-clockwise moments about the same point. If a body is in equilibrium, then the sum of the clockwise moments is equal to the sum of the anti-clockwise moments about the same point. So what am I trying to say? If a body is in equilibrium, what is equilibrium? If this body is balanced, for example, if this happens to be a meter rule, and a meter rule ranges from 0 to 100 centimeters. Let me show you a meter rule. Okay, sorry, we are back. Now, this is a meter rule. This is a meter rule. So it ranges from 1, I can say from 0, you can see it now, to 100. Okay, this is a meter rule. So let's assume that this is a meter rule. Okay, now for it to be balanced, use what we call a knife edge. This is a knife edge. Can you see it? This is a knife edge. If I place it here on a horizontal, if I keep it on a table, keep this on a table, then place it like this, it's going to be balanced, right? It's going to be balanced. So that is what they're trying to say, that if a body is in equilibrium, being in equilibrium means this side is equal to this. Now that this body can now stay on this knife edge without falling. Do you understand? It means that this body can now stay on this knife edge without what? Falling. It's because I'm holding it. It's supposed to stand firm when it is placed at 50. And 50 is the what? Center of gravity. That is the midpoint of this meter rule, because this meter rule ranges from 0 to 100. So the middle of 100 is 50. So if I place this meter rule on this knife edge and it is kept for a while, it's going to be what? Balanced horizontally. It's because my hand is not a horizontal table, so it cannot be like balanced. Do you understand? Okay, so this is what I'm trying to say. If this body is in equilibrium, that is the body being in equilibrium. Okay, then the sum of the clockwise moments must be equal to the sum of the anti-clockwise moments. Now, what do I mean by that? I have set of masses I want to show you. These are the set of masses. Okay, if this is balanced at 50, let's assume it's balanced because it's supposed to balance. Now, if I put a weight here, okay, this weight is acting down. That is what you are seeing, that is going down. So if you see this weight acting down, what are you going to do? You are going to make sure it balances the other one. And you see now, this weight is taking this meter to fall on this other side. Okay, that means this side has more weight than the other. So I'm going to balance it, okay, by placing another one here. Now, when you place another one, it's going to do what? It's going to still remain balanced or lying horizontally. So the principle of moment is trying to tell us that if this body is in equilibrium, both of them having two different weights on this side and on the other side, they are going to be what? In equilibrium. Then the sum of the clockwise moments must be equal to the sum of the anti-clockwise moments. What do I mean? Now, I have placed this mass here. This mass is a mass of 100 kg, right? I've placed this mass of 100 kg here. Now the distance covered here, this is 50. I have to note the distance here. This is 93. So the distance between this and this, what's the difference? This is 50, this is 93. The difference between this and this becomes what? That is 93 minus 50 to give me what? I'm going to get 43. That's the difference. Do you understand? So, and that is the distance from here to here, right? And the other one is the distance from here to here. So I'm still going to, sorry, I'm still going to use it to explain further. I just want to explain this principle of moment, that if a body is in equilibrium, so equilibrium means when a body balances horizontally with two weights on both sides. Okay, now this is the knife edge. I've shown you what is the knife edge. Then the sum of the clockwise moment is equal to the sum of the anti-clockwise moments, about the same point. Now what is clockwise? With your stopwatch, it's going this way, right? That is clockwise because it is moving the direction of a clock. So this is clockwise moment, right? Why this one is what? Anti-clockwise moment. So from the principle of moment, the moment from here to here is equal to the moment from here to here. And what is the moment from here to here? I will now say clockwise moment is equal to 60 times from here to here is B. So 60 what? B, right? Then anti-clockwise moment is equal to 20 times what? A. So 20 times what? A. So if it's in equilibrium, it means that 60B is equal to 20 what? A. So clockwise moment is equal to anti-clockwise moment. All right. So I hope you understand what I just explained. That if a body is in equilibrium, I've shown you the body. In equilibrium means we have a knife edge on a missile rule. We have, sorry, a missile rule on a knife edge with the masses hanged on both sides. So what you're considering is where the mass was hung, the distance from the center. This is the knife edge that I showed you. Knife edge. Okay, distance from here to here is what you're going to consider. First, you're going to balance the meter rule, and then the distance from where the mass was hung to the center. You subtract it, and also the same way you subtract it. Okay, so you're going to see several problems, several ways in which this can come as a question to you as a student. So I'm going to explain all of that. Bosede, thank you so much. Please give it a thumbs up. I really appreciate. Thank you so much for joining. triangle is pivoted at its midpoint, okay? C, with a vertical force of 10 Newton hanging from the distance 30 centimeters from C. At what distance must a 15 Newton force hang to balance the ruler horizontally? Now, for us to look at this question, this is a meter rule. And I told that meter rule ranges from what? From 0 to 100. And this is a pivot. We call it knife edge. Now, this pivot is at its midpoint. So you are going to place it at its center, which is what? 50. So it can balance horizontally. Can you see it now? It has balanced what? Horizontally, right? It's because my hand is not firm. If not, it should be lying what? Horizontally. That means it is balanced, right? Okay. So then after that, he said a vertical force of 10 Newton hanging from a distance 30 centimeters from C. So if you check from here, we are going to see a vertical distance of 30 centimeters. Now, if here is what? Here is what? This is 50. That is the midpoint. So for us to hang, we are going to hang it at a distance of 30 what? Centimeters, right? So I'm going to use the diagram to explain what I'm trying to say. So we drew a sketch. Now, okay, this is not long. Let me extend this. Now the midpoint, this is 0 and this is 100, right? Now the midpoint is C. And that C is what? 50 centimeters. That is the middle of the meter rule. Okay? Okay, let's go. With a vertical force of 10 Newton hanging from the distance of 30 centimeters from C. Now, this is what? C. Then from here, we're going to hang it at where? From here to have a distance of what? 30. We hang it here. Now, if you are calculating the distance from here to here, that is 30 centimeters, right? That means I'm going to hang it at 20 centimeters. So that the difference between 50 and 20 is going to give me what? 30. Do you understand? They say the distance from C to where this 10 Newton force was hung is 30. So if it is 30, where do we hang it? From here to here, it's going to be 20. So the distance between is going to give me what? 30. So let me write this well so I can see it clearly. This is at what distance, okay, must a 15 Newton force hang to balance the ruler horizontally? Now we have another force on the other side because I've showed you an illustration. If we hang a particular mass on one side, it's going to move this side, right? For example, this is what I mean. This is my 50, that is the center of gravity or the midpoint of this. You see, it's floating. But as soon as I put this is a weight. As soon as I put it on this, I'm going to see what will happen. It will start bending. It will not even allow me to leave it go. Let it go, sorry. I'm looking at it. It's going down. It's pulling it down. Because of what? It is not balanced. Nothing was kept on the other side. But as soon as I bring another force, which is a weight, and put it here, you see how it's going to be? You see that it's going to do what? It's going to balance. Can you see it now? Can you see it now? All right, so that is what they are trying to tell us. They want us to tell them the distance. They are going to hang this 15 Newton force, but we don't know the distance. This is 15 Newton. The distance is what? The distance is x. The distance is x. So how do we find the distance? But we already have the force. That is where the knowledge of the principle of moments will now come into play, which says that if a body is in equilibrium, that means, or then, it means that the sum of the clockwise moments, why the same moment is because it can be more than one that will be clockwise, is equals to the sum of the anti-clockwise what moments at the same point. Okay, so this is clockwise, while this is anti-clockwise. Okay, so the clockwise moment here is 15 times the distance from here to here is what? X. And that is what you are looking for. So we say 15 times x is equals to, this is 10 times distance from here to here is what? 30. I will say 10 times what? 30. Do you understand? When I multiply, I have 15x is equals to 300, right? Because I'm looking for x, I'm going to say that, okay, divide both sides by what? By 15. This will cancel to be left with what? X. So this is 300 over 15. X is equal to what? It's going to give me 20 centimeter. So my x is equal to 20 centimeter. So this is how we can use the principle of moment to solve problems. Certain they're going to give you one side and ask you to find the other what? The other side. I hope you understand. So let's look at more few examples under this particular concept. All right. Now, look at this diagram. We are asked to calculate the magnitude of what? E. Now, let me just say, the question is, calculate the magnitude of E. E is a force. Now, how do we do that? Look at the question. Is this somehow advanced to what we just did before? But it's still the same thing. This is, which one is clockwise, which one is anti-clockwise? The clock is always going this way. This is clockwise moment, right? Now, this is the middle. From here to the center, this is the distance from here to here for this force of 80 Newton. Now, this one is acting up, and it's not going to come down to act through this side. So it becomes what? Anti-clockwise moment. So this is what? Anti-clockwise moment. So I'm going to explain to you in the next slide. I'm going to explain again positive and negative moments so I can understand this one proper. Now, if you are this, the distance will be from here to this pivot. So the distance here will now be what? 2.5 plus what? 0.5, right? Because moment is the first and perpendicular distance. Okay, so let's go. Clockwise moment is equals to anti-clockwise moment. That is 80 times from here to here. From here to the pivot, we have a distance of what? 0.5 is equals to, then E, that is what you are looking for, times the distance is from here to this pivot. And I have 2.5 plus 0.5, right? So let's use our calculator. Certainly, this is going to give me what? 40 is equals to, this is E times 0.5 plus 2.5 plus 0.5 is going to give you what? 3. So 40 is equals to 3 what? E. Now let's divide. We divide both sides by what? By 3 to get the coefficient of E. This cancel this will have what? I have E. Then 40 divided by 3. So my answer becomes 13.33 watts Newton. So this is how we can solve this kind of problem. This is acting down, but the other one is acting up. Any vector acting up, if you are trying to resolve it with respect to moment, it becomes clockwise moment. I'll tell you why. So I'm going to look at now a negative moment. Understand when two are acting up and acting down. So you can be able 50 plus live. Thank you so much for coming. Please give this live a thumbs up, double tap on your screen. Thank you so much. Now, look at this. That is still under clockwise and anti-clockwise moment. Now, this F is the force. And the distance from here to here, we're going to subtract. Okay? So this is what? Clockwise moment. Why this is what? Anti-clockwise moment. So what do we do now? The clockwise moment is equals to anti-clockwise moment. Okay? So we have the force times the distance from here to here, right? So I'm going to say 90 minus 45 is equals to 30 bracket difference between this and that is 45 minus 15. Now, we work it out. So this is F times, this is going to give me what? 45 is equals to 30 times what? 30, right? Okay, because 45 minus 15 is 30. So let's work it out. This is going to give me 45F is equals to, I have 900. So I divide both sides by the coefficient of 40. This cancelled it to be left with what? F. 45 into itself 1. Into 90, I have what? 2. So I have the force to be 20 Newton. Do you understand? So clockwise moment, that is from here to the center of the meter rule. Difference between this and this is 90 minus 45 to give us what? Anti-clockwise moment, that is the force, which is 30. So and the difference between this and this, that is 45 minus 15 to have this, right? By the time you subtract, you get 45. So this is 30 times 45 minus 15 is going to give me 45. You bring it down. So this is 45 F is equal to this time it is 900. So I divide both sides by the coefficient of F, which is 45 by itself to give us F. 45 by 900 to give us what? 20. So this is how we can solve this problem using the principle of clockwise, the principle of moment, which is clockwise moment equals what? Anti-clockwise. you can hear me. The weather is not too good. We have positive and negative moments. If we have this positive and negative moments, look at this diagram. These are forces acting at different points. Okay? But our target here is to make respect to the center, which is the pivot, right? That is our target. These are our targets. Okay? So remember the principle of moments. Clockwise equals anti-clockwise moments. Okay? So looking at this one is acting to the clockwise direction. So it's going this way. So this is clockwise moment, right? This one too is acting. So this is clockwise moment. Okay? And the distance from this is A3. The distance from this to the pivot, that is the A4. All right. Now look at this one. These two are what? Anti-clockwise to the pivot because it's acting this way. Okay? So I'll have this. This is anti-clockwise moment. This is anti-clockwise moment. So distance from this P1 to the pivot is A1. Distance from this to the pivot is A2. Now, look at this F5. Where is it going? Any moment that has crossed this pivot and is up. So this one is what? Going anti-clockwise. So the anti-clockwise will continue from here. You understand? This is like a clock. So it will continue from here to be what? Anti-clockwise. Now this clockwise, once it crosses this pivot, another clockwise we're going to have will be from here to this way. That is clockwise. So if that is the case, this becomes what? Anti-clockwise moments. I don't know if you understand. So these two are clockwise to this pivot, while this and this are what? Anti-clockwise. Because once it crosses this pivot, it's going to revolve again from here to the what? Anti-clockwise. So from the principle of moments, we are going to analyze it this way to state all the clockwise moments together and the clockwise moments together. So let's go. Clockwise moment is equal to F3 and distance is what? A3. That is F3 dot A3 plus F4 dot A4. The two of them are what? Clockwise moments, okay? Then anti-clockwise is equal to F1. The distance is from here to that is A1. I will say F1 dot A1 plus F2 dot A2, right? These two are anti-clockwise. Then plus this plus F5 dot A5. Now from the principle of moment, if clockwise moment is equal to anti-clockwise moment, so what do we say? What do we say? We say that F3 dot A3 plus F4 dot A4 is equal to F1 dot A1 plus F2 dot A2 plus F5 dot A5, right? Then I can carry these other ones to this side. So have F3 dot A3 plus F4 dot A4, okay, minus F1 dot A1 minus F2 dot A2 minus F5 dot A5 is now equals what? To 0. Now I brought all these ones to this side to equate them to 0. Do we understand? So with this, you can solve any moment that are acting up and that are acting what? Down. And don't forget, any clockwise moment that crosses these pivots, it's not under clockwise, it will be clockwise from here. That is if we have a vector up. Then any anti-clockwise that has crosses these people, it's no longer anti-clockwise, it's continuing from where? From up, because this is just like a rotation. Do we understand? All right, so let's look at a few examples of how we can apply this principle. All right. Now looking at what we have. Now this is a JAMB question. Let me write it here. This JAMB 1979. Okay, let me say. Okay, so we have this question and we are expected to solve it. To find the value of W, I have this pivot here. Then I have W acting down. I have T, which is the force of 20 newton acting upwards. Then the distance from this T to this point, where the pivot was hung, is 1 meters. Then distance from this weight, where this was hung, is 1 meters. Okay? So we have to find the value of W. So one thing that will come to your mind is, how is this weight? How are they going? Which is clockwise, which is anti-clockwise? So if you have that at the back of your mind, you realize that this W is what? Clockwise, because this is the pivot. We are making respect to this pivot. So if you are making respect to this pivot, from here, turning this way becomes clockwise. So I will go this way. This is clockwise moment. Now, I told you anything up that is acting this way becomes what? Anti-clockwise. So this pivot, this tension of 20 newton is acting towards the pivot. So it becomes anti-clockwise moment. So from the principle of moment, this is equals to this. So let's go. We say clockwise moment is equals to anti-clockwise moment. Okay, so what do we have? The clockwise moment is W, and the distance from here to the pivot, that is 1 plus 1. Do we understand? Because we are making respect to this pivot from here to the pivot, and the distance from here to here is 1. From here to here is 1. That will give us 2. Okay? That's the distance between this W and what? The pivot. So we have W times, this is 1 plus 1 now. That's my total distance. Okay, then is equals to, the tension T is acting anti-clockwise. So we are going from here to here, becomes 1. So if you go by that, we are going to say this is W times 1 plus 1 is what? 2. This is times 2 is equals to 20 times 1 becomes what? 20. So we proceed by saying this is 20W is equals to what? This is 2W is equals to 20. We now divide both sides by what? By 2. Okay? Coefficient of W to give me what? W. 2 into itself 1. 2 into 20, I have what? 10. So the answer becomes 10 Newton. So whenever a force is acting up, you should make respect to that is acting up. So that is becomes anti-clockwise moment. Looking at the position where the pivot is arranged. If it is arranged this way, it's going to be what? Clockwise moment. So our attention is to look at the position of the pivot where it is placed to know whether you are going clockwise or you are going what? Anti-clockwise. Okay, now we are going to look at this particular example now. What are we looking for? Okay, let me see what you are looking for. Express T in terms of F. Okay, the question says, uh, the question said that we should express T in terms of what? F. So we are actually looking for T, okay? But we're going to leave it in terms of F because they didn't give us the value of F. All right, so what do? Clockwise moment equals what? Anti-clockwise moment. Okay, let me just read out the question so that we can understand. A uniform light beam, SZ is hinged at X and kept in equilibrium. So that means this is where the pivot is. And we call it what? X. It's and kept in equilibrium by the forces T and F as shown in the diagram above. If X0, that X0, okay, equals 20 centimeter, and they wrote 200 here for me, so let me change it. And this one is what? 30, okay? And OY equals 30 centimeter. Express T in terms of what? F. This is a JAMB question 1997. This is JAMB 1997. JAMB, okay? All right. So we are making respect to this, okay? That is where the bench is clipped. So that is where it is pivoted, okay? We are making respect to that point. So that becomes clockwise moment and what? Anti-clockwise moment. So I'm looking for T. But before we can do that, look at this. This is inclined and we need a vertical vector. So I'm going to resolve it, okay, to the vertical. If we resolve it to the vertical, it's going to be what? T cos 30, right? It's going to be T cos 30 because we're resolving to the, to the vertical is what? Sine. It's going to be T sine what? 30 because we're resolving to the vertical and we are working with the vertical vector, okay? All right, so that is by the way. So the next thing we're going to do is to resolve it with respect to this. That is, this is clockwise moment. Why this is what? Anti-clockwise moment, okay? The clockwise moment is F and the distance is 20 plus this because we're making respect to this pivot here. Then anti-clockwise moment is this. The distance is from here to here, that is 20. So if you go by that, we can solve what you are looking for. So let's go. So we say that this is what? F. Okay, let me just say clockwise moment is equals to anti-clockwise moment. So that is F times distance is 30 plus 20 is equals to T sine theta because we have resolved it to the what? Vertical. T sine theta bracket, distance from here to here is 20. Okay, so let's solve. This is F times 30 plus 20 is going to give me what? 50. Okay, now So there is a mistake. This is sine 30 bracket what? 20. Sorry. So I will have t sine 30 is 0.5, okay, times what? 20. Now this is equals to 50f, okay, equals what? What do we have? This cancel this, right? Then I have 10. I have 10. Okay, better still I will say t times what? 10. Because I am looking for what? For t, and I'm expressing t in terms of f. So I'm going to divide both sides by what? Coefficient of t, which is 10. So I divide both sides by coefficient of t, which is 10. Okay, this will cancel this to give you what? 5. Therefore, my t is equals to 5f. Do you understand? Now, what I did was to make reference of this resolving going to the what? Clockwise moment, while this is what? Anti-clockwise. And I have to resolve it to the vertical, so I can use the vertical vector to solve. And that is what I have. Then, the clockwise moment is what? F. Distance from here to here, so we calculate 20 plus 30 to have 50. Okay? Why this distance is from here to here to have what? 20. Then you open up to say sine 30 to be this, multiply by this to have what? 10. We divide both sides by the coefficient of t to get t as what? 5f. Now, we have the measurement of an object by the principle of moment. Now, how do we measure an object using the principle of moment? We can do that if an object is balanced. Now, I was making respect to this meter rule. It ranges from 0 to what? 100. Okay? Now, we now get to a point that we already know that the half of 100 is 50. That is, but even by layman know that half of 100 is 50. But then, you now realize that this meter rule, instead of it to be pivoted at 50, they will now put the pivot at 40. And the question says, what is the mass of the meter rule? That kind of a question, how can you answer it? But you already know that the midpoint of this meter rule is 50. Why did they now put this pivot on 40? This is a meter rule, a force of Q. You know already that the midpoint of a meter rule is 50. They now put it either or lower or greater than 50. And you're asked to find the weight or the mass of this meter rule. What are you going to do? You are going to put the weight of the meter rule on the proper place or on that particular point that is meant to be. For example, if from here to here is 100, 0 to what? 100, and they hung a mass of 10 grams on this side, okay? This becomes what? 40. They now put a pivot. And you're asked to find the mass or the weight, because mass and weight is related. With mass, you can get weight. With weight, you can get mass. I will tell you how it is related. We are now asked to find the mass or the weight of this meter rule. You don't need to stress yourself, since you already know that meter rule has a balance point of 50 centimeter. Just put the mass or the weight, whichever one you're looking for, at the 50 cm mark. That is the rightful center of gravity of this meter rule. Do you understand my point? That if you place it here, because this is the rightful center and not this, they want to use this principle of moment to get the weight or the mass of a meter rule or any object that is lying horizontally. That is the essence of measurement of an object by the principle of moment. If this is kept at 40 and we are expected to find the mass or the weight of that object, what are we going to do? In as much as we know that this object has a center of 50 centimeter, you're just going to put that mass at 50 centimeter. And we use clockwise moment equals what? Anti-clockwise. So this is clockwise, this is what? Anti-clockwise. So the distance from here to here is what? 50 minus 40. So give me 10. Now, if this is 10, distance from give me 30. Okay? With that, I can find the unknown, which is what? Which is 10. That is what we have this board. So if this is hung here, what you are going to do is to place that weight of the object on the rightful point, the rightful center of gravity, the midpoint. Do we understand? If the question says a half meter rule, you know that a meter rule, look at it, 0 to 100, okay? What's the half? The half is what? 50. But if the question says a uniform half meter rule, that means I'm working with from 0 to what? 50 is no longer what? Complete. Now let me ask you, the half or the midpoint of a half meter will be what? This will be 25, because I'm working with from 0 to 50. So half of 50 becomes what? 25. Okay? So I'm going to bring out some questions under this to see how we can apply this to get the weight or the mass of any object given to us. All right? All right. So looking at this question, let's look at it. It says a uniform meter rule, that is a meter rule, the one that is complete, balances on a knife edge, okay, at the 55 centimeter mark when a mass of 40 grams is hung from 95 centimeter rule, balances on a knife edge at the 55 centimeter mark. Okay, let's quickly look at this question. A uniform meter rule of mass 90 grams is pivoted at the 40 cm mark. If the rule is in equilibrium with an unknown mass m placed at the 10 cm mark and a 72 gram mass at the 70 cm mark, determine what? M. For us to do that, let us draw our meter rule. Okay, our meter rule of mass is 90 grams, pivoted at 40 cm mark. This is 0, this is 100. So the pivot is at what? 40. Okay. Then if the rule is in equilibrium with an unknown mass m, place at 10 cm. So this is 10 cm, you place a mass m, okay? And a 72 gram mass at the 70 cm, this is 70 cm, you place as a mass of what? 72. Now, determine m. Now, this mass of a meter rule should be placed at the rightful center, which is 50. So we place the mass of what? 70 what? Gram. Okay? So that leads us to clockwise and what? Anti-clockwise. This is what? Clockwise moment. This is clockwise moment. Why this is what? Anti-clockwise moment. Okay? I'm going to end this screen very soon because my battery is seriously going down. So what do? We say clockwise moment equals anti-clockwise. That is 90 times difference between this and this. So I will say 90 times what? 10 plus 72 times 30. Okay? 72, that is this. And distance between this and this is 30. Then is equals to m. Time difference between this and this is what? 30. Okay? So I'm going to multiply to get what? 900 plus, this is 72 times 30. I'm going to have 2160 is equals to 30 what? M. If I add then plus 900, I'm going to have 3060 is equals to 30 M. I'll divide both sides by the coefficient of 30. Okay? Divide by 30. So therefore, my M is equal to 102 what? Gram. So this is how we can solve this problem under the principle of moments. I hope you understand it. Okay? Please, if you are joining us for the first time, don't forget to subscribe to this channel because we are going to be doing live Saturdays and Sundays, same time, 2 p.m. Okay? And if you have any question you want me to answer, you can drop it in my comment section. See you next time in my next class. Bye.